So, now we look at the idea of the length of the vector. We just saw that a vector is basically something which is talking about displacement, it is going to have a direction and it is also going to have a length or a magnitude. So, what we are going to do is we are going to look at the length of the vector. Now, what do we mean by saying length of a vector? So, let us do a simple recall. So, recall that if A is a point in some coordinate which coordinate let us say x naught comma y naught, and assume that we want to move from A to B, from A to B whose coordinates are given by let us say x naught plus B 1 and y naught plus V 2. So, how does that look like graphically? It is going to be like this. Let us say I have my E 1 axis, I have my E 2 axis. I basically have this point A, let me call this as this point A, which is given by x naught y naught, and I have this point which is B, which is given by x naught plus B 1 y naught plus V 2, and this is the distance that we have travelled. So, what are we trying to look at? We know that the vector, let us call this as the vector V. So, we know that the vector V is given by the let us say the vector A B, where we know how to compute the vector. We look at x naught plus V 1 y naught plus V 2 minus x naught y naught, and what we get? We basically get V 1 V 2, and that is the vector V, which is basically given by V 1 V 2. Now, we also note something very interesting here. What is that? From the point A, we have actually gone a distance of V 1 along the E 1 axis and V 2 along the E 2 axis, and what we find out is that these two are perpendicular to each other and you actually have a right angle triangle form. Therefore, I know by Pythagoras theorem I can find out by Pythagoras theorem we can find out the length of the hypotenuse, where the hypotenuse square, we know that hypotenuse square is equal to the adjacent square plus opposite square in a right angle triangle. In a right angle triangle, we know this. So, what is the hypotenuse square? The hypotenuse square is basically what we are going to notate it as, let us say we are going to give a different notation for this. We are going to call this as V square, where this corresponds to the norm of the vector V, or the length of the vector V. Norm of the vector V, which is also the length of vector V, yeah, and that is the basically the distance that we are talking about, length of vector V. And how is it given? By Pythagoras theorem we know that this is equal to V 1 square plus V 2 square, and we also know that therefore, the length of V, the distance that we have travelled, is basically square root of V 1 square plus V 2 square. Now, this is what we are going to call it as the Euclidean norm. This is what we are going to call as the Euclidean norm of the vector V. We will also see this from a different perspective. When we do inner products and dot product, we will look at the norm of the vector in terms of that. Right now we have used the idea of Pythagoras theorem and we have got the magnitude of the vector. So, this is also called the magnitude of the vector v. Now, suppose if we scale the vector v, we already saw that we can do the operation of scaling. Suppose we scale the vector v by, let us say, a factor k, by a factor k, that means the resultant vector is going to be k times v. So, what is the magnitude of this? So, magnitude of k v is nothing but square root of k square v 1 square plus k square v 2 square is the magnitude of k v, and we know that we can pull out the square root of k square outside. So, this is going to be magnitude, this is going to be absolute value of k into the norm of the vector v, and this is a very important result where we are going to say that the magnitude of a scaled version of a vector is nothing but the absolute value of the scaling factor into the vector's norm. So, one interesting thing that we observe here is we take the absolute value of k, that means even if you are going to scale use a scaling factor which is going to be negative, we are going to take the absolute value for the simple reason that the length is going to be a non-negative quantity. The length is always a non-negative quantity, and what we see is therefore, this absolute k makes sense there, right. Now, suppose we want to find out a unit vector, we want a unit vector in the direction of v, unit vector along the direction of v. It means we will put it this way. So, how are we going to find out? Let me call that as, let us say, let u be a unit vector along v. So, how are we going to define this? We are going to say u is basically the vector v divided by the norm of the vector v. This is what we are going to call as a normalized vector. This is what we are going to call as a normalized vector, and what is interesting is the norm or the vector length or the length of the vector u is always 1. Let us take an example and see if that actually makes sense. So, let us look at consider a vector v which is given by, let us say, 3 4. Now, what is the norm of this vector? Let us first of all figure out how that looks geometrically. So, 1 2 3 4 5, let us say 1 2 3 4 5, 3 4 is a vector which is going to be here, that is going to be the 3 4 vector which is going to be v. So, I have 3 here and I have 4 over there. Now, we again use the Pythagoras theorem, we see that this is going to be square root of 3 square plus 4 square, and that gives me 5 units, right. Now, if I want to get the unit vector out of this, what do we have? The unit vector u is given by the vector v divided by its length, which means I am going to have v divided by the length of v. Every component is going to change now, every component is going to become 3 by 5 and 4 by 5. So, this is going to be my u vector. Let us check if this u vector has length 1. So, this is going to be square root of 3 by 5 the whole square plus 4 by 5 the whole square, which is essentially square root of 25 by 25, which is 1. So, you get a unit vector. Yeah. Now, as I said, let us make a formal statement here. Since norm of V is a measure of length, it measures length, we are going to say since norm V measures length, we are going to say that norm of V is greater than or equal to 0. This is what we said, the length of the vector is a non-negative quantity. So, the question is when is norm of this vector V equal to 0? We just figured out that recall norm of V was V square was V1 square plus V2 square. What we see here is this implies this is sum of squares, and sum of squares is always greater than or equal to 0. When will it be 0? It will be 0, it is 0 if and only if both V1 and V2 are 0. What does this mean? This means the vector V has both its components to be 0, in which case this is called as the 0 vector. So, what are we going to say? We are going to say that the length of the vector, the length of a vector is 0 if and only if vector is 0 if and only if it is a 0 vector. If and only if it is the 0 vector. What do we mean by that? We say that all the components are 0 here. That means all components of the vector are 0. Okay. Now, let us take a very interesting case here, where I want to look at I want to look at some unit vectors. Let us look at some examples of unit vectors. Now, what do we mean by some examples of unit vectors? Let me take this vector V, which is nothing but 1 0. Now, what is the norm of this vector V? This is 1. This is my first example. Let me take this second example, where I am going to look at the same vector V, but I am going to change this to this. I am going to get again the norm of this vector, which is again equal to 1. Let me take this third vector, which I am going to take as 1 by root 2, 1 by root 2. Now, again we will see this norm of this vector is equal to square root of 1 by root 2 square plus 1 by root 2 square, which is square root of 1 by 2 plus 1 by 2, which is 1. So, that is also a unit vector. Let me take one more case where I look at this. where V is going to be minus 1 0. This also has the norm which is equal to 1. Let us take this case where I am going to define V to be this vector 0 minus 1. Here also we are going to have the norm of this vector to be equal to 1, and therefore, we have different representations of that. We will have different unit vectors that you can have, and what I am going to do is I am going to look at the let us say we are going to look at the unit vectors, look at all the unit vectors that emanate, all the unit vectors that emanate from the origin. Right, in let us say in 2D plane. Okay. In that 2D plane. So, what are we going to get? What is the geometry that is formed? So, what is the geometry here that we get? The geometry we get will be is the unit circle. And unit circle is one of the most important idea that you would come across if you are going to do the Z transform or something in domains like signal processing. So, this corresponds to the unit circle. Now, what is interesting is we can actually capture the idea of, we can also obtain the notion of or obtain the length of the vector, obtain the length of a vector using the idea of dot product or inner product, which we will see later, or the inner product. This we will see in the subsequent lectures that we are going to have. So, to conclude this lecture, what is it that we have seen? We have seen that the length of the vector can be obtained using Pythagoras theorem. Length of a vector, which we call as the Euclidean norm, denoted as V, we call this as the Euclidean norm. Yeah, Euclidean norm, which can be obtained using Pythagoras theorem. And we saw that the length or the norm of the vector V is always greater than or equal to 0. It is 0 if and only if all the components, if and only if vector V is the 0 vector, and we also looked at the idea of unit vectors, which is basically normalized vectors. Normalized vectors, and we also looked at the geometry of unit vectors from geometry of unit vectors emanating from the origin is the unit circle. Is the unit circle. Now, in the next lecture, what we will do is we will look at how do we combine vectors, how do we combine vectors. What it is it to say combine vectors? So, what is it to say combine vectors, and we look at the idea of linear combinations of vectors and we move on to the ideas of dot product and the angle between vectors and so on. Thank you.